for flavor mixing. And Pontokoro, how do I, the neutrino mixing is PMNS, Pontokoro Makinagawa Sakata, PMNS. Respectively. Okay. So today we will go through what we call the CKM matrix or matrices. Before we start with the CKM matrix, let us historically describe the origin of the Cabibbo angle. So, Cabibbo in 1963 proposed this already during that time, that he proposed that that there could be a mixing between down and charm. So propose that down and charm quark can mix. Cos theta C D plus sin theta C S. The reason is because, why we all know, because in quantum mechanics the square of the coefficient, which is VUD square plus VUS square must be equal to 1. So it is obvious that cos square plus sin square equal to 1. So he just, saya ingat budak sekolah pun boleh buat apa ni, this equation. And then how to get the Cabibbo angle? Very straightforward. You know that theta C, which is the Cabibbo angle, is just the inverse of the tangent of the angle, and that is just the inverse of the VUS divided by the VUD. And experimentally it was found to be about 13.02 degrees. Later, of course, when charm was discovered, when charm quark was discovered, they people start writing, the D dash is cos theta C D plus VUS S. That no problem, but the S dash is a mixture of minus sign delta C D plus cos theta C S. Sorry. So this means that this implies that you can write D dash S dash equal to VUD VUS VCD VCS GS. Obvious, there are not 4 quark, 6, there are 6 quark. Masa tu top dan bottom tak dijumpai lagi. Jadi Kobayashi and Maskawa saya tak ingat. Saya rasa Kobayashi ni dia punya postdoc, Maskawa ni professor So propose apa ni, generalization D dash S dash V dash equal to VUD VUS VUB bottom VCD VCS VCD and VTD VTS VTB TSB. So basically, how do you, of course, this VUD and so on, they have experimental value. I don't want to write it here because it is too long, but you can roughly, so this is the CKM matrix. And the degree of mixing is measured by the amplitude of the VUD. So VUD describe the degree of mixing. The smaller that value, the smaller is the mixing. And you will see that the strongest mixing is along the diagonal. When you real or experimental determined values is roughly about 0.97, 0.22, 0.0035, and then 0.225, 0.973, 0.0412, then 0.0087, 0.0404, and finally 0.999. So the degree of mix, so the V values tell you about the strength of the mixing. And you can define this if you draw what you call up type mixing, so you have up, jump, top on one side, and then you have the down, strange, and the bottom here. So these are the down type. Okay, at the bottom, and here the interaction tend here to be strong. So the strong interaction character, and here weak interaction character. Okay, what does it mean? It means that these three tend to show a strong interaction character, okay? Whereas this quark here give you a weak interaction character. And mixing is of course across the board. There is none that is zero here. So all possible mixing is possible, except that the strength of the mixing is different. So all mixing is possible. Okay. Anyway. What is what you call if you, because these are, we all know that here when you when you square the amplitude, it has to be equal to 1 because it is a probability. So the CKM matrix try to so the constraint of unitarity of the matrix can be generalized well on diagonal term. So this can be written as just our k alone, then this is V I K for a particular quark. Okay, kita boleh campurkan semua for a particular quark. So katakan this quark is strange. I could be anything. Up, down, jump, apa-apalah I. Sorry, for a given I, for a given I but different K. Maknanya I itu katakan up, katakan I is up, and then K could be anything. Down, strange, jump, apa semua. So you campurkan tu, then similarly it could be just the I and you vary the K, doesn't matter. That must be 1. Okay. So the constraint just like that. Okay. So all the V square must add up to 1. for all generation I. This implies that the sum of all coupling of any of the up-type quark or the all down quark is the same for all generation. This is called weak universality. So this relation is sometimes called weak universality. The reason why is because you will see that it is strongest in the weak, this mixing. That's why you have DSP, which is DSP, not the UCT. Okay? Walaupun ada juga CTU, semua ada. Tapi tidak diserlahkan di situ. Okay. There is another constraint of unitarity, so-called. Selain daripada, actually this just reflect apa? Reflect that the probabilities, all the amplitude square or the probability semua dicampurkan mesti equal to 1. Cannot be more than 1 or less than 1. Because it is all the possible probabilities. But there is another one called the what you call it, orthogonality. So this involves the unitary triangle. Kind of orthogonality. What does that mean? The summation of, say, a K, V, I, K, V, J, K. So, example, I cannot show all the unitarity triangle. This is say BD, bottom down. Anything yang down type, it could be S, could be a BS or a DS. So this BD unitary triangle. Formed from, say, VUD, V star UB plus VCD, V star CD plus VTD, V star TB, and this equal 0. I mean, so how do you plot it? So this angle is say gamma, alpha, and beta, and this could be a pi 1, this could be a pi 2, and this could be a pi 3. It doesn't matter whether you use alpha, beta, and gamma. So, but at the end here, you have the possibility of getting a row and meson. And the length of this triangle here is VTD, VTD, alpha. So this alpha is 89 degrees. Gamma is 68 degrees. And beta is 180 minus 89 minus 68 lah. Berapa? Experimentally. And this you can sort of look up at the Feynman diagram. What are the type of Feynman diagram that give you the interaction between U and V? So, I mean, to be consistent, you do 3 experiments. So, for example, for UV, you know, you have to have a B quark. So you have to do a quark line diagram, and then you have to have say a U, or doesn't matter. You can. I'm trying to write the anti-quark dotted, yeah? Doesn't matter lah, dotted. So this will be a B, and this is a U bar. So all the anti-quark saya akan tulis dotted. And then here, where they interact, will produce a W minus, and this W minus decay into a lepton and an anti-neutrino. Anti-neutrino of the lepton. So this lepton could be electron, muon, or tau. So where is the VUV? It is here. The amplitude of this. So the VUV is in this vertex. Okay. So it's a probability of that interaction to occur. Or you can lukisan ni tak bagus. Neutrino, anti-neutrino of lepton, and this is lepton, W minus, and then this is B, and this is U. So of course, this is the vertex of VUV. And then this one, anti-quark. So this is the trajectory of any anti-quark. Or you can, so in these first two involve lepton. So these two, apa ni? I better write it A, B. This involving interaction. Sebab apa? W. Okay, melibatkan W. But here you will see, walaupun dia melibatkan W, dia sebetulnya adalah strong interaction. Here, I will. This is anti-quark. This B here become a U by emitting W minus. Obviously, again, this give you the V U P, but here the decay is into a B and a U bar C. So this involves strong interaction, weak interaction, weak interaction. So you kena kata orang tu buat 3 eksperimen ni dan dapatkan average. So you have to look at all the possible vertex for VUB and average from the measurement. And what is even more important is to put in place some CP violating phase.